Hello to everyone watching on YouTube. This is Guru Prerana Shabadi, and in this short talk, I'm going to be presenting some of the work I did over the summer and in the last few months while I was working with Professor Sergio Mover at the Department of Computer Science in my university, which is Ecole Polytechnique. So this research experience was my first foray into the world of formal verification and hybrid systems. And I had a lot of fun discovering the things that I did. And I hope through this talk, you will be able to share some of the excitement that I experienced. So this is a re-recording of a talk I had given about 2 months back on my work at a reunion of many research groups from around France at my university, who are all working in the areas of around formal methods. And the talk itself was also a really great experience for me, sharing my ideas and my work with multiple experienced researchers and getting their feedback and their questions was a really fun experience for me. So let's start off. So my work focused on accounting for communication delays arising in hybrid systems. I believe that this is best explained through an example, which will make it immediately clear what I was trying to do. So let's jump straight into that. Consider the problem of trying to control drones, which are navigating in space towards their destinations. But we have to ensure that the drones avoid collisions with each other. Now, if you look at this image here, these tiny triangles represent the drones, and the blue region around them is what we don't want intersecting with each other. Now, in order to avoid collisions, the drones need to communicate their positions, velocities, and the direction in which they're headed in with each other at all times, so that the drones can coordinate with each other and we can successfully avoid a collision. Now, inevitably, when you have communication involved, you need to use a medium or a protocol for communication. And here, in any real world setting, we are sure to have some delays associated to these communication protocols. And these delays are what we are trying to model and account for and see how they affect the system. So one of our main motivation to consider hybrid systems was this paper here, where they present a hybrid automaton model for each of the drones. And they prove theoretically that this model for each drone, and if it is controlled by a given control policy, would successfully avoid collisions, and each of the drone would be able to reach its destination theoretically. But of course, one strong assumption they make is that there are no communication delays at all, and each drone has perfect information about all the drones around it. Well, communication delays within this hybrid system is what we will be trying to model. Now, just to give a short recap about what a hybrid automaton is. So a hybrid automaton is a model for a system, and it can be very useful to model systems which are specifically controlled by software, and for example, robots or other embedded systems. And hybrid automata allow us to capture both discrete time behavior and continuous time behavior. let us look at the definition of a hybrid automaton. So hybrid automaton is made up of some set of system variables. These system variables just represent the state of the system. For example, in the case of the drone, this could be the positions, the velocity, the direction of heading, etc. And they have a set of discrete modes or locations. Now, if you look at this tiny example hybrid automaton here, it has two discrete modes, accelerate and decelerate. And each of the discrete modes has an associated invariant. The invariant is simply a predicate over the system variables, and it states some property which holds to be true whenever the hybrid automaton in its during its execution, it's at a particular location. The invariant over the system variables holds true. For example, here in the accelerate location, we have the invariant that v2 is greater than or equal to 10. Now, this means that during a state of execution of the hybrid automaton, the system variable v2 is always greater than or equal to 10 whenever the system is in the accelerate location. And we have a set of transitions between the discrete locations. In this case, we have two transitions, one going from accelerate to decelerate, and another going from decelerate to accelerate. And we have some continuous time behavior within each of the discrete locations described by a set of differential equations. These basically model how each of the system variables evolve when the system is in each of these two discrete locations. Now, associated to each of the transitions, we also have a guard set and a reset map, which basically set up some conditions on the system variables to check whether a transition would be allowed or not at a particular moment of time. Here in this case, we have that a guard condition that v2 is less than 10 for this transition from accelerate to decelerate. It means that the system can switch from accelerate to decelerate only if the system variable v2 is below 10. Now, this was a quick overview of what a hybrid automaton is. Now, what we observe is that, okay, here we're going back to the hybrid automaton model proposed for the collision avoidance for drones in this paper here. Now, within this hybrid automaton model, as I mentioned before, they assume that there are no communication delays and that each drone has perfect information about the drones around it. Now, what this means in terms of the hybrid automaton is that, for example, initially all the drones would be in the location straight, which means that they are flying straight towards their destination. But as soon as some other drone comes close to it within a particular distance, it needs to switch to a hold, which means stop flying or stop moving. But we are trying to see what happens if there was a delay in knowing the position of the other drone by within the system, and this transition cannot take place immediately. Now, here we have to note that the positions of the other drones are not system variables within our system, but they appear as inputs within our hybrid automaton. In some cases, these models are more known as input-output hybrid automaton, but we just stick to the terminology hybrid automaton because it's simpler. So now let us try to understand the nature of the delays that we are trying to model. This is very important because what our eventual goal is to try to extend the model or the semantic of a hybrid automaton to allow us to capture delays. To understand the nature of the delays that we are trying to model, let us jump to another example. Here, in this very toy example, very simple example, we have two cars, and we are trying to control this car, which is following this green car. This can be considered as a very oversimplified cruise control problem. The orange car needs to be controlled so that it maintains minimum distance from the leading green car, and we want to ensure that by observing the velocity and the position of the leading car, we are able to avoid the orange car from colliding with the green car. Now, we propose this oversimplified hybrid automaton to model the orange car, and we claim that with this hybrid automaton model, collisions can be avoided, although this might not necessarily be true, but that's okay. We are just trying to play around with the hybrid automaton model itself. It doesn't matter if whether the system is eventually safe or not in the strict sense. But anyway, in this hybrid automaton model, we have two locations, accelerate and decelerate. This is the hybrid automaton model we saw a bit earlier. Basically, when the leading car has a velocity of greater than 10, we ask the orange car to accelerate with constant acceleration of 3. And when the leading car's velocity dips below 10, we ask the orange car to start decelerating, and we nullify the acceleration. So, and again, the orange car can again start accelerating when the velocity of the leading car goes above 10. So this is our hybrid automaton model for the orange car to help the orange car avoid collision with the green car. Now suppose we introduce delays in observing the position and the velocity of the leading green car. Now this would mean that we cannot immediately jump from the accelerate location to the decelerate location when the velocity of the leading car dips below 10. We would have some delay associated to observing the velocity of the leading car, which is in this case v2. And when we have this delay, the orange car cannot shift from the discrete location accelerate to decelerate immediately. There would be some delay. Now this highlights a very important point about the nature of the delays. It is that the delays in the observation, they do not affect the dynamics within a discrete location. That is, if you see within the dynamics of each discrete location, it only describes the dynamics of the orange car. Here, there are no delays absolutely at all within the dynamics of each discrete location. The only place where the delays have an effect is on the transitions. That is, since we have delays on the observation of the velocity of the leading car, and we have a guard condition upon the transitions, which depends on the variables of the leading car, green car. This affects the transitions that we might need to take between the discrete locations. This is a very important point which is crucial. Just give me a second. I need to plug in my laptop. So this highlights a very crucial point about the type of delays that we are trying to model, in the sense that they only affect which discrete mode we are in, and not the dynamics within each system. So now, I mentioned earlier that our final objective was to extend the semantic of a hybrid automaton to capture these delays in the observation of some input variables in some sense. So what we did was we introduced a semantic for a hybrid automaton called the lazy hybrid automaton. Here, what we did was we extended the definition or the semantic of the hybrid automaton, and in addition to what we had before in a hybrid automaton, we introduced a set of input variables. Now, these input variables are simply variables which don't evolve, or their dynamics is not described in our system. That is, the differential equations do not guide the evolution of these system variables, but they evolve in some other systems, and they only appear to us as inputs. And now what we add is a set of time bounds associated to each input variable. Now these time bounds represent the delays associated to each of these input variable, the observation delays. Now let us go ahead and try to understand how these time bounds function in practice. Now, in order to capture the delays, we need to introduce a different semantic for the guard evaluation of transitions. Basically, we need to allow the guard condition to be satisfied even if there is a delay on the observation of some input system variables, and we need to still allow this transition to take place. Now, in a regular hybrid automaton, at some given moment, we can take a transition between two discrete locations if the system variables evaluated at a given time t satisfies the guard condition of the transitions. Now, we translate this in with the lazy hybrid automata, and we say that we can take a transition between two discrete locations if there exists some times in the past within the given time bounds associated to each input system variables, such that each of these system variables evaluated at these different times satisfies the guard conditions. Now, this is how we model the delays. That is, instead of evaluating the system variables at the current instance of time, we evaluate them at an instant in the past, which in some sense captures the delay, if you can see it. It's not really complicated to see that having a delay in the observation of a variable directly translates to the fact that we are observing the past value uh, of that system variable. Now, this is what we make use of to model these delays. Now, intuitively, let us try to see when the guard condition would be satisfied in the case of our oversimplified cruise control hybrid automaton model. Now, suppose we have a 3-second up to a 3-second delay in observing the velocity of the leading car, which in our case is v2. And we say that we can switch from the discrete location accelerate to decelerate if there exists some So as I was saying, we can take a transition from accelerate to decelerate if there was some time t prime within the past 3 seconds, such that the velocity v2 at this time t prime was less than 10. Now, this again intuitively captures the delay on the observation of the velocity v2, in the sense that we are evaluating it at a time in the past, which means that this system is observing a past value of the velocity v2. Now here you can notice that we don't have a fixed delay on v2, and the only thing we are ensured is that we have at least one value of v2 recorded by the system within the past 3 seconds, and we are allowed to take a transition from accelerate to decelerate if there was some time in the past 3 seconds where the velocity v2 dipped below 10. Now we need to do the same translation of the evaluation with the invariants, because since we cannot observe the value of the system variables at an exact instance of time, we also need to introduce the delays within the invariants. And here we say that the invariant holds across time horizon of execution if the variables evaluated at time t satisfy the invariant. But in the case of a lazy hybrid automaton, again, at each time the invariant holds if there was some point in the past where the system variables evaluated at that point in the past satisfied the invariant. Now, let us quickly look at an example trace in a lazy hybrid automaton. The trace here just means an execution of the lazy hybrid automaton when we run it in some sense. So suppose we fix the dynamics of V2 to evolve at a constant rate of -1, starting from an initial value of 16. That is, at time t equals to 0, the value of V2 is 15, and it reduces at a constant rate of -1. So at time t, the velocity V2 would be given by 15 minus t. And initially, the velocity and position of the orange car, the car we are trying to control, are both 0. And initially, we are in the mode accelerate. Now, the orange car can continue to stay within the state accelerate until t equals 6, for example, because the invariant is satisfied for all t in 0 in the interval 0, 6. Now notice in particular that after t equals 5, the velocity of the leading car V2 does indeed dip below 10. That is, starting from 5, it goes below 10. But within our lazy hybrid automaton model, since we are allowed to evaluate the value of V2 at a point in the past, this is not a problem, because from time t equals 5 to 6, since we can look up to 2 seconds in the past of the observation of V2, at some point in the past 2 seconds, the value of V2 was indeed greater than or equal to 10. So we can continue to stay in the mode accelerate. And at time t equals 6, we can switch to the mode decelerate. Now here, because the guard condition is indeed satisfied that V2 was less than 10. Now here we saw that we stayed in the mode accelerate even longer than when the velocity of V2 was greater than or equal to 10. What this intuitively means is that there was a delay in the observation of V2, and we ended up taking the transition to decelerate slower than expected. Now, I hope that made things clear about what we are trying to model and the nature of the delays that we have on our hands here. Now, the next challenges after we finished defining the semantic of a lazy hybrid automaton was to understand the expressive power of the model. And in particular, what we were trying to do is we were trying to see if we can translate these extended set of features of the lazy hybrid automaton, if there was some way to capture these additional behavior within a regular hybrid automaton. But we saw that in the general case, the lazy hybrid automaton is extremely complex, and it demonstrates some behavior which would be which we claim that is impossible to capture in a regular hybrid automaton. So we had to place some restrictions slash assumptions on the lazy hybrid automaton to indeed allow these translations into regular hybrid automata to take place. Now, what do I mean by translations? Basically, what I mean is that if we are given a lazy hybrid automaton, I'm trying to see if there's a somewhat equivalent regular hybrid automaton, like original hybrid automaton, which can capture the exact same execution traces as our lazy hybrid automaton. Now, we do indeed have some results on the translations. Let us quickly have a look at them. Now, when we are trying to translate lazy hybrid automaton, what we can capture within the translation is the new guard evaluation semantic, which was the delayed guard evaluation semantic, basically, which allows us to evaluate our system variables at a point in the past. But what does not work is that we need to introduce this condition on the transitions, which we call the almost non-zero condition. Basically, we need an upper bound on the number of transition that can take place within any given time period. And this is a fixed upper bound on the number of transitions. And we also do not have invariants. We cannot translate invariants within our translation. Now again, let us demonstrate this translation using an example. Now here we again go back to our oversimplified cruise control example automaton. And here you notice that we have removed the invariants on the two discrete locations. And again, suppose that we have up to a 2-second delay in the observation or the communication of the value of the velocity of the leading car, which is V2. And since we need the almost non-zero conditions, we impose that there can be at most 3 transitions in any given 2-second window. That is, within any period of 2 seconds, there can be at most 3 transitions which can take place within this hybrid automaton. Now, when we translate it, so here I have shown the translation, and here we have the parallel composition of 2 regular hybrid automaton. Now these are not lazy hybrid automaton. This is just the parallel composition of 2 regular hybrid automaton. What the parallel composition means is just means that when we have an execution of the hybrid automaton, these 2 automata just run parallelly with each other, and this can observe the variables of this, and this automaton can observe the variables of this automaton. Now basically here we just have a parallelly running hybrid automaton, which at some random points in time simply captures the value of the variable V2. It evolves independently from this automaton here, and we simply save the state or the value of V2 within this automaton here, so that we can use the saved value of V2 in the past within the guard conditions of our automaton. Now, if we have the saved values of V2 from the past, then we can account for the delays on the observation of the state of V2. Now here you notice that I put question marks on these guard conditions, just because we need to translate the guard conditions that we had previously. Previously we had a guard condition from accelerate to decelerate that V2 has to be less than 10. Now when translated with these delays and using the saved values of V2 in the parallelly running automaton, basically what we need to check is that whether V2 was less than 10 at some point within the past 2 seconds. Now this can be easily achieved because we have saved the states of V2 at some points and we can check whether any of these saved states was less than 10. Here S1, S2, S3 just represent the value of V2 at some point in the past, and the time in the past when it was recorded is represented by TS1, TS2, and TS3. And we check that if the TS1 is less than 2 and whether S1 was less than 10, then indeed we can take the transition. Now here you notice that this upper bound, the almost non-zero condition that we had, that was an at most 3 transitions in any given 2-second window, directly translates to the fact that we have three states in this parallelly running automaton. Now, if we don't have these restrictions, if we allowed an unlimited number of transitions within a given time period, then this would be extremely difficult to capture in a finite state automaton, almost impossible, because we would need to store an infinite number of values of V2. Now here, since we have the upper bound, we can safely save it. So now we also see that invariants are extremely hard to capture within the translations, and this is simply because we cannot hope to store every value taken on by a variable within the given continuous time bounds. We would need to essentially store an uncountable number of values of a variable within the given delay period, and this is impossible in a finite state automaton. Again, as I just mentioned, it's the same problem with removing the almost non-zero condition. It would be extremely hard to capture within a regular hybrid automaton if we remove this condition. And this is our main motivation to claim that a complete translation from a lazy hybrid automaton into a regular hybrid automaton is in fact impossible, although we have not proven this fact. Now, we also have another result of the translation of lazy timed automata. Here, what I mean by lazy timed automata is just that a timed automata is basically a hybrid automaton where all the system variables evolve as clocks. That is, all of the system variables evolve at a constant rate of 1 in any given discrete locations. Now here, within lazy timed automata, when we have delays in the observation of specific clock variables that we have in lazy timed automata, we can indeed capture the invariants within the translation along with the new guard semantic, but we still need the almost non-zero condition on the as an upper bound on the number of transitions. I won't go into too much detail about why we can translate the invariants now, but a basic motivation or intuition is that since all of these variables now evolve at a constant rate, we can exactly determine what the value of a specific clock was in the past delay period. Again, within this translation of timed automaton, for a given example here, we have a parallelly running automaton, which basically captures the resets on on a given variable, and we track all of the resets that happened within the delay period, which can help us do something very strong, which is that we can compute every value held by a system variable. In this case, it's a clock y in the past 10 seconds. And if we can compute every value of a system variable within the given delay period, then we can indeed set up the invariants to also work within within the translation. So now, just to summarize the results of the translations that we have, we saw that we can translate lazy timed automata into regular timed automata, provided we have the almost non-zero condition as an upper bound on the number of transitions. And we can translate lazy hybrid automata into regular hybrid automata when we have the almost non-zero conditions, and also we remove the invariants. Now, when we placed some additional restrictions on the evolution of the variables, that is, we made all of the system variables to evolve at a constant rate. We made them clocks in timed automata. We were able to capture the invariants. But again, this is a restriction that we have. Now, to summarize, lazy hybrid automata allow us to capture delays in the observation of input variables within hybrid systems. And these input variables do not affect the dynamics within the system, but only affect which discrete mode or location that we are present in. And these lazy hybrid automata allow us to take a transition between these locations based on state held by the variables at some point in the past, which capture the delays in the observation of these variables. However, we saw that it was extremely difficult to capture invariants within the translation of lazy hybrid automata into hybrid automata when we tried to capture the enlarged behavior of a lazy hybrid automata within a regular hybrid automata, which also led us to hypothesize that lazy hybrid automata are strictly more expressive than standard hybrid automata. Again, this fact has not been proved. And some of the future directions for work and ideas that I have would be to firstly perhaps introduce delays within the dynamics as well. That is, when we have delays in the observation of variables which do evolve within our system, then this would mean that the differential equations would depend on the value of a system variable held in the past, which would lead us towards considering delayed differential equations, or DDEs, within each discrete location, and also seeking a proof of the fact that lazy hybrid automata are strictly more expressive than hybrid automata. And another thing that would be interesting to understand is the relationship between the continuous semantic of lazy hybrid automata and the discrete semantic of lazy hybrid automata, which was presented in an earlier paper by these authors. So what I did not mention is that our lazy hybrid automata model was strongly inspired by the lazy hybrid automata presented in this paper here. But a strong difference is that we consider continuous time semantic of evolution of the system, whereas they consider a discrete semantic of the lazy happy automata. But I would want to discover how we can relate these two, and whether one can help obtain results on the other. But that was quite a brief. Okay, maybe that wasn't entirely brief, but it was a description nonetheless of the work I did over the past few months, and hope you had as much fun as I did playing around with drawings of automata. And that's it from me. Thank you so much.